Hello, this is the presentation for this paper, Robustness-Oriented K-edge cell placement. This is my name and my email address. If you have any questions about this paper, please feel free to send me an email. Now for the ESP is also called edge cell placement in this presentation. This is the outline of this presentation. First, we will give you some briefly introduction and one example here. Then we will focus on the problem formulation. Next part, we will design two algorithms, and the next one, we will experimentally evaluate the performance of these two approaches. Last one, we will conclude this work and point out the future work. Now let's go to the first part, the mobile edge computing. We all know it is an extension of the cloud computing. In the mobile computing systems, edge users can access to the content in a low latency manner. This is because edge servers are usually deployed at the close to the users, but each edge servers are usually suffers from different kind of failures, such as cyber attack. So, to make sure all the users can use this service or can access to the content smoothly, the edge servers need to be deployed in a robustness manner. Now this is an example here. In an area there are 8 base stations here. If we want to place 6 of the edge servers on this 8 base station, one direct strategy as shown in Figure B, we can place these 6 edge servers on these 8 base stations to maximize the overall coverage. But from this one, you can see if one of the edge server fails to serve its users, nearly no other edge servers can take over all of the users in this failure coverage. So the robustness in this strategy is poor. In the Figure C, if we place the edge servers in these edge base stations, we will see the intersected area in this figure is much larger than this part. So if one of the edge server fails to serve its users, the users who are located in this intersected area can be taken over by other edge servers. So the robustness in this strategy is much higher than the Figure B. Now for the problem, it means we want to place k edge servers on n base stations to maximize the overall robustness. So it's also called KESP problem in this paper. And in this paper, we firstly take into account robustness in ESP problem and formulate it as a constraint optimization problem. Next, we proposed two approaches, one optimal approach for the small-scale ESP problem, and another is approximation approach for the large-scale ESP problem. Last one, we have conducted extensive experiments to evaluate the performance of these two approaches. Now let's go to the problem formulation. The general models for the n base stations and k edge servers. For robustness, we use the PET to model this robustness. Its definition can be found here. Based on this definition, the robustness can be calculated by the equation 1. In equation 1, the robustness is calculated by the coverage area of base station I and base station J. S I and J is the intersected area between base station BI and BJ. This is the one robustness between a pair of base stations. If we put all of the robustness together, it should be a metric here. Then we will, based on the robustness, we can define the neighbor base stations. If two base stations has an intersected area, it means Si and J not equal to 0. These two base stations are called neighbor base stations. is donated by n. Bi is bi's neighbors. Also bi, we can also use bj equals means bj's neighbors. Based on the formulation above, we can summarize the problem here. Maximize the overall robustness with two constraints. The first one, the robustness should be part of the matrix, and the total number of the edge servers should no greater than the number of base stations here. Now for the algorithms, the first one is the optimal approach to maximize this objective with two constraints. We deploy this optimal approach by using IBM Cplex. For these tools, it can be found from the paper and also can be found from the online. It's an open source IBM tools. For the second one is algorithm design to approximation approach. Now this is the approximation approach, which includes two parts. For the second part, it is a part of the first one. You can see in the line 13. We deployed this approach by using Java based on the Windows OS. Now I will give you the approximation ratio because it's approximation method. So we now analyze its approximation ratio. We will use one lemma and one theorem to analyze the approximation ratio. The details proof can be found from the paper. Now we will not discuss here. If you have any questions about the proof, please send me an email. Now this is an example of the approximation approach. Give a base station here as shown, the same as the motivation example. If we take the B7 at the start, then we use algorithm 1, we will find all B7's neighbors. If B7's neighbors and B7 has enough base station to deploy the k edge servers, okay, the algorithm is done, is finished. If not, we will use algorithm to find more base stations to deploy the edge servers. Based on these procedures, the time complexity of this approximation can be analyzed as follows. We suppose each base station has at most m neighbor base stations, then its time complexity is here. To experimentally evaluate the performance of these two approaches, we conduct the experiments based on public dataset. This dataset can be found from the paper as well. For the experiment settings, we use this table to test the performance of these two approaches based on two sets of experiments. The first one is a small one. Is a small scale experiment settings, and the large one based on three parameters: the number of base stations, the coverage of each base station, and the number of edge servers. Based on these settings, the experiment result can be shown as follows. The results include two parts. The first one is effectiveness and the second one is efficiency. From these figures, we can see the optimal approach can find the best solution, but its time consumption is much higher than the other approach. So for the small scale ESP problem, we can use the optimal to find the solution, but for the large scale ESP problem, we may use the approximation approach. Now this is the conclusion. In this paper, we propose two approaches to solve this new problem, and then we have tested the performance based on two set of experiments of these two approaches. In the future, we will investigate the trade-off between the robustness and the coverage. This is because in this paper, we only focus on the robustness. Thus, in the future, we will trade off these two metrics. Okay, thanks all for listening. That's all.